Right now, somewhere in the depths of space, two black holes are spiraling toward each other in a cosmic death dance that began millions of years ago. In less than a second, they will collide with such violence that space itself will ring like a bell, sending gravitational waves racing across the universe at the speed of light. But here's what makes this moment truly disturbing. When these two objects merge, something impossible happens to one of the most fundamental laws in physics. For over a century, we've believed that entropy, the measure of disorder in the universe, can only increase or stay the same, never decrease. This isn't just some academic rule. It's the iron law that governs why your coffee gets cold, why your phone battery dies, and why the universe itself is slowly dying a heat death. But when black holes merge, something extraordinary occurs that challenges everything we thought we knew about the nature of reality itself. Consider this: each black hole carries an enormous amount of entropy, proportional to the area of its event horizon. When two black holes with entropy values of, say, 1077 and 1076 units respectively merge, basic physics demands the combined system must have at least 1077 units of entropy. Yet sophisticated computer simulations and direct observations from LIGO reveal something remarkable: the final black hole's entropy often exceeds this minimum by factors we're still struggling to understand. Tonight we're diving into one of the most profound questions in modern physics. How does the merger of two black holes not only preserve entropy, but dramatically increase it in ways that reveal hidden connections between gravity, quantum mechanics, and the fundamental structure of spacetime itself? The answer will take us from the event horizons of colliding giants to the quantum foam that bubbles beneath reality, and ultimately to a new understanding of what entropy really means in our universe. Stephen Hawking revolutionized our understanding when he proved that black holes have temperature and emit radiation. Jacob Bekenstein showed us that black hole entropy is proportional to surface area, not volume. But it took the groundbreaking LIGO detection starting in 2015 to give us real data about what happens when these cosmic monsters actually collide. What we discovered defied our expectations and opened entirely new questions about the nature of information, energy, and the arrow of time itself. The implications stretch far beyond black holes. Understanding entropy increase during mergers could unlock secrets about the Big Bang, reveal whether information can truly be destroyed, and even explain why time moves forward instead of backward. We're not just talking about exotic physics in distant galaxies, we're exploring principles that govern everything from the formation of consciousness to the ultimate fate of our universe. As we embark on this journey, you'll discover why Einstein called black holes dark stars, how objects with no physical surface can have temperature and entropy, and why the merger process releases more energy than the nuclear fusion of all stars in the observable universe combined. You'll understand how gravitational waves carry away information, why the final black hole spins faster than either of its parents, and how this reveals profound truths about the conservation of angular momentum, energy, and something far more mysterious: information itself. But perhaps most remarkably, you'll see how these cosmic collisions serve as natural laboratories for testing our deepest theories about reality, places where general relativity, quantum mechanics, and thermodynamics converge in ways we can observe, measure, and begin to comprehend. If you're fascinated by the intersection of cosmic phenomena and fundamental physics, subscribe and hit the thumbs up button. And here's a question that will frame our entire exploration: if entropy must always increase, what happens to the information that falls into a black hole when it merges with another? Comment below with your thoughts. I'll pin the most insightful answer, because this question touches the very heart of what we'll uncover together. The journey we're about to take will challenge your understanding of space-time, energy, and information. We'll witness the most violent events in the universe through the lens of thermodynamics, and discover how these cosmic catastrophes actually reveal some of the most elegant and beautiful principles in all of physics. From the quantum mechanical origins of black hole radiation to the large-scale structure of spacetime itself, we'll uncover why black hole mergers represent not just cosmic destruction, but cosmic creation, the birth of new understanding about our universe's deepest laws. Now let's begin by understanding what entropy actually means and why its behavior during black hole mergers has revolutionized our understanding of physics itself. Chapter 1: Hidden Order. The word entropy carries an almost mystical weight in physics, yet most people fundamentally misunderstand what it actually means. We're told it's disorder. And while that's not entirely wrong, it misses the profound beauty of what entropy really represents: the number of different ways a system can arrange itself while maintaining the same observable properties. Imagine a box containing 1 trillion identical gas molecules. At any given moment, you can measure the box's temperature and pressure. But what you can't see is the incredible dance happening at the molecular level. Each molecule zips around with its own unique position and velocity. Yet somehow this chaos produces the predictable, measurable properties we observe. Entropy counts how many different microscopic arrangements of those molecules could produce the same macroscopic temperature and pressure you measure. The revolutionary insight came in the 1870s when Ludwig Boltzmann derived his famous equation, S equals K log W, where S is entropy, K is Boltzmann's constant, and W represents the number of possible microscopic arrangements. This wasn't just mathematical elegance, it was a window into the statistical nature of reality itself. Every macroscopic property you observe emerges from countless microscopic possibilities, and entropy measures the vastness of that hidden landscape. But here's where black holes shattered our understanding. They appear to have no internal structure whatsoever. Einstein's general relativity describes them as regions where spacetime curves so dramatically that nothing, not matter, not light, not information, can escape once it crosses the event horizon. The no-hair theorem tells us that black holes are characterized by only 3 properties: mass, electric charge, and angular momentum. Everything else, every detail about the matter that formed the black hole or fell into it, should be completely erased. This creates what seemed like an impossible paradox. If black holes have no internal structure, how can they have entropy? What microscopic arrangements could possibly exist in a region described by such elegant mathematical simplicity? The answer would require decades to emerge and would fundamentally change our understanding of both gravity and quantum mechanics. The breakthrough came when Jacob Bekenstein, then a Princeton graduate student, made a startling proposal in 1972. He suggested that black holes must have entropy, and that this entropy should be proportional not to their volume as it is for ordinary matter, but to the surface area of their event horizon. This was revolutionary because it implied that all the information about a black hole's internal structure is somehow encoded on its two-dimensional surface, like a hologram. Bekenstein's insight emerged from a simple thought experiment. Imagine lowering a hot object toward a black hole's event horizon. As the object approaches, its temperature appears to increase due to gravitational redshift effects, while the outside observer sees its energy contributing to the black hole's mass. If black holes had no entropy, you could violate the second law of thermodynamics by disposing of entropy-carrying matter. Therefore, Bekenstein reasoned, black holes must have entropy to preserve this fundamental law. Stephen Hawking initially resisted this idea, arguing that if black holes have entropy, they must also have temperature, and objects with temperature must radiate energy. Since nothing can escape a black hole's event horizon, he reasoned, they couldn't possibly have temperature. But in 1974, Hawking's own calculations proved him wrong in the most spectacular way imaginable. Using quantum field theory in curved spacetime, Hawking discovered that black holes do indeed radiate energy. The quantum vacuum near the event horizon bubbles with virtual particle pairs that briefly pop into existence before annihilating each other. Occasionally, one particle from such a pair falls into the black hole while its partner escapes, carrying away energy and gradually causing the black hole to shrink. This Hawking radiation gives black holes a precise temperature inversely related to their mass. The mathematics was stunning in its precision. A black hole's temperature equals dc cubed 8 gmk_b, where the symbols represent fundamental constants and m is the black hole's mass. For a black hole with the mass of our Sun, this temperature is a mere 60 billionths of a degree above absolute zero, incredibly cold, yet definitively real. More massive black holes are even colder. While hypothetical microscopic black holes would burn with temperatures exceeding the core of the hottest stars, equally remarkable was the confirmation of Bekenstein's area law. The entropy of a black hole equals F4L_p squared, where is the area of the event horizon and L_p is the Planck length, approximately 10 meters. For a solar mass black hole, this entropy is approximately 10, a number so vast it's nearly incomprehensible. To put this in perspective, all the entropy in the visible universe outside of black holes is estimated to be around 10, dominated by the roughly 10 supermassive black holes lurking at the centers of galaxies. This discovery revealed something profound about the nature of spacetime itself, if black hole entropy is proportional to surface area rather than volume. It suggests that all the information that appears three-dimensional to us might actually be encoded on two-dimensional surfaces. This insight would later evolve into the holographic principle, one of the most revolutionary concepts in modern theoretical physics. But understanding black hole entropy raises an even deeper question. What exactly are the microscopic states that this entropy counts in ordinary matter? We can identify the individual particles and their arrangements for black holes, described by the smooth geometry of general relativity. No such microscopic constituents seem to exist. This puzzle points toward a fundamental gap in our understanding, one that quantum gravity theories like string theory and loop quantum gravity are desperately trying to fill. The implications extend far beyond academic curiosity. Black hole entropy connects the macroscopic world of general relativity with the microscopic world of quantum mechanics in ways we are still discovering. It suggests that spacetime itself might be granular at the smallest scales, composed of discrete units that can be counted and arranged. Some theories propose these units might be quantum strings, others suggest they're discrete geometric structures, but all agree that black hole entropy points toward a deeper, more fundamental description of reality. As we'll see, when two black holes merge, this already mind-bending concept of entropy becomes even more extraordinary. The merger process doesn't just preserve the entropy of the individual black holes, it dramatically amplifies it through mechanisms that reveal new connections between gravity, quantum mechanics, and information theory. The stage is now set for understanding why black hole mergers represent some of the most profound events in physics. These aren't just cosmic crashes, they're laboratories where the fundamental laws of thermodynamics, general relativity, and quantum mechanics converge in observable, measurable ways that continue to surprise and illuminate our understanding of the universe itself. Chapter 2: Cosmic Dance. To black holes don't simply collide like cosmic billiard balls. Their approach toward each other is a ballet of spacetime that can span millions or billions of years, a gravitational courtship that begins when they race separated by vast distances and ends in a merger so violent it releases more energy in gravitational waves than all the stars in the observable universe emit in light. The dance begins long before the black holes can significantly influence each other's structure. Perhaps they formed from a binary star system where both massive stars collapsed within a few million years of each other. Or maybe they were supermassive black holes residing at the centers of galaxies that collided and eventually found each other across cosmic time. Regardless of their origin, once they're gravitationally bound, the laws of physics dictate an inevitable spiral toward merger. Initially, their orbital motion is slow and stately. At distances of thousands or millions of times their event horizon radii, they circle each other like distant planets, losing energy through the emission of gravitational waves so weak they carry away only tiny amounts of orbital energy. Einstein's general relativity predicts this energy loss with mathematical precision, describing how accelerating masses distort spacetime and send ripples racing outward at light speed. These gravitational waves represent something unprecedented in physics: direct radiation of spacetime curvature itself. And like electromagnetic waves, which are disturbances in electric and magnetic fields, gravitational waves are disturbances in the very fabric of space and time. As they pass through any region, they alternately stretch and compress distances in perpendicular directions, creating a characteristic pattern that carries information about their source across cosmic distances. The crucial insight for understanding entropy comes from recognizing what these waves carry away: energy. Certainly this is what causes the orbital decay. Angular momentum as well. This is why the orbital period gradually decreases. But buried in the complex waveform patterns is something far more subtle and profound: information about the internal structure and quantum state of the merging black holes themselves. As the black holes spiral closer, their dance accelerates dramatically. What took millions of years at large distances now happens in mere hours, then minutes, then seconds. The mathematics of this in-spiral phase follow the post-Newtonian approximation to Einstein's field equations, describing how the orbital parameters evolve as energy and angular momentum flow away in gravitatio. No radiation. When the black holes reach a separation of roughly 10 times their event horizon radii, something remarkable happens. They begin to significantly distort each other's spacetime geometry. The circular symmetry that characterizes isolated black holes breaks down as tidal forces stretch and deform the event horizons. This is where perturbation theory reaches its limits, and we must turn to full numerical relativity supercomputer simulations that solve Einstein's field equations without approximation. The final moments before merger reveal the most extraordinary behavior. The black holes orbit each other several times per second, their event horizons visibly elongating and oscillating. The gravitational wave emission reaches a crescendo, carrying away energy at a rate that briefly exceeds the luminosity of all stars in the observable universe combined. Yet these waves remain invisible to ordinary matter, passing through planets, stars, and galaxies as if they weren't there. During this final in-spiral, each black hole's individual entropy remains approximately constant. The Hawking radiation that normally allows entropy to fluctuate operates on timescales vastly longer than the merger process. From the perspective of black hole thermodynamics, the in-spiral preserves the entropy of each individual black hole while the system as a whole loses energy and angular momentum to gravitational radiant ion. But entropy is more than just the sum of its parts. The merging system develops correlations and entanglements between the quantum states of the two black holes that didn't exist when they were widely separated. These quantum correlations represent a form of information that contributes to the total entropy of the system, and their behavior during merger remains one of the most active areas of research in black hole physics. The moment of merger itself, when the event horizons first touch, marks a transition from the well-understood in-spiral phase to the chaotic plunge and ring down that follow. Numerical relativity simulations reveal that this contact creates a bridge of highly curved spacetime connecting the two black holes, followed rapidly by the formation of a single, distorted event horizon encompassing both original black holes. The newly formed event horizon is far from spherical. It rides and oscillates like a soap bubble in the wind, gradually settling into the characteristic spherical shape of an isolated black hole through a process called ring down. During this settling, the black hole emits gravitational waves at specific frequencies determined by its mass and angular momentum, like a struck bell ringing at its natural resonant frequencies. These quasi-normal modes, as physicists call them, represent the black hole's attempt to reach equilibrium. The frequencies and decay rates of these oscillations encode fundamental information about the black hole's properties and provide crucial tests of general relativity in the strong field regime. More importantly for our story, they reveal how the final black hole's entropy relates to the entropies of its progenitors. The ring-down phase typically lasts only milliseconds, but during this brief time, something remarkable happens to the entropy budget. The final black hole always has less mass than the sum of its progenitors because significant energy was radiated away in gravitational waves during the merger. Yet its entropy proportional to the area of its event horizon nearly always exceeds the sum of the original entropies. This entropy increase isn't a violation of thermodynamics. It's a demonstration of thermodynamics operating in the most extreme possible environment. The merger process converts gravitational binding energy into both gravitational radiation and internal black hole entropy. The system as a whole satisfies the second law of thermodynamics. But the distribution of entropy between radiation and the final black hole reveals profound truths about the nature of information and energy in strong gravitational fields. Understanding exactly how this entropy increase occurs requires diving into the quantum mechanics of horizons, the information content of gravitational waves, and the holographic encoding of information on event horizon surfaces. The merger process serves as a natural experiment testing our deepest theories about gravity, quantum mechanics, and thermodynamics simultaneously. What makes this especially remarkable is that we can now observe these mergers directly through gravitational wave detectors like LIGO and Virgo. Each detection provides real data about entropy increase during black hole mergers, allowing us to test theoretical predictions against observation for the first time in history. These measurements are revealing that black hole mergers are not just cosmic catastrophes, they ray windows into the fundamental structure of spacetime itself. The dance of merging black holes thus represents far more than cosmic destruction. It's a process of cosmic information processing, energy redistribution, and entropy generation that illuminates some of the deepest questions in physics, as we'll see. Understanding how entropy increases during these mergers requires us to think about black holes not as empty voids, but as the universe's most efficient information storage and processing systems. Chapter 3: Impossible Energy. The numbers involved in black hole mergers are so staggering they challenge our ability to comprehend them, yet behind these cosmic energies lies an elegant mathematical precision that reveals profound truths about the nature of mass, energy, and information itself. When LIGO first detected gravitational waves from merging black holes on September 14, 2015, humanity witnessed the conversion of pure mass into pure energy on a scale that dwarfs anything else in the known universe. Consider the first detected merger, now known as GW150914, to black holes with masses approximately 36 and 29 times that of our Sun, spiraled together over billions of years before merging in a cataclysmic finale that lasted mere milliseconds. In those final moments, roughly 3 solar masses of pure matter equivalent to the mass of 600 trillion kilograms simply vanished, converted directly into gravitational wave energy according to Einstein's E=mc. To grasp the scale of this energy release, imagine that every single atom in the Sun could be converted to pure energy in a fraction of a second. The gravitational waves from GW150914 carried away energy equivalent to converting 3 entire solar masses, but they did so in just milliseconds. At the peak of the merger, the power output in gravitational waves exceeded the combined luminosity of every single star in the observable universe by a factor of 50. This energy conversion reveals something fundamental about the nature of black hole entropy and its relationship to mass and energy. When do black holes merge? The final black hole has less mass than the sum of its components because binding energy has been radiated away. Yet despite this mass loss, the final black hole has more entropy than either of its progenitors. This apparent paradox resolves only when we understand that entropy can increase even as total energy decreases, provided the energy is redistributed in ways that increase the number of possible microscopic states. The mechanism behind this energy release lies in the binding energy of the two-body gravitational system. Like electrons bound in an atom or protons and neutrons bound in a nucleus, two black holes orbiting each other exist in a bound state with negative binding energy. The closer they orbit, the more tightly bound they become, and the more energy must be radiated away to reach even lower energy states. But unlike atomic or nuclear binding energies, the gravitational binding energy of black holes scales with their total mass in a way that produces truly cosmic energies. For two equal mass black holes, the binding energy at merger approaches roughly 10% of their total rest mass energy. When that rest mass is measured in solar masses, the resulting energy release reaches levels that can briefly outshine entire galaxy clusters. The mathematics describing this energy extraction follows from the most fundamental principles of general relativity. Einstein's field equations describe how mass and energy curve spacetime, while the geodesic equations describe how objects move through that curved spacetime. When do black holes orbit each other? They follow geodesics in the curved spacetime they collectively create, gradually spiraling inward as energy radiates away in gravitational waves. The rate of energy loss follows precise mathematical formulas first derived by Peters and Matthews in 1963, building on earlier work by Einstein and others. For circular orbits in the weak field limit, the power radiated in gravitational waves equals 30 to 5 times gc times a combination of the masses and orbital parameters. As the black holes spiral closer, this power increases rapidly, following a runaway process that culminates in the violent merger we observe. Yet the most remarkable aspect of this energy release isn't its magnitude, it's its purity. The energy emerges as gravitational radiation, carrying away no material particles, no charged particles, no ordinary matter of any kind. Gravitational waves are disturbances in spacetime itself, representing perhaps the purest form of energy release possible in our universe. This purity has profound implications for understanding how entropy increases during the merger process. And like other forms of energy radiation, gravitational waves carry away information in a very specific way. The complex waveforms encode details about the masses, spins, and orbital parameters of the merging black holes. More subtly, they may carry information about the internal quantum states of the black holes themselves, information that contributes to the total entropy budget of the system. The extraction of gravitational binding energy during merger also reveals deep connections between classical general relativity and quantum thermodynamics. The energy that flows away in gravitational waves comes from the reduction of gravitational potential energy as the black holes approach each other. This energy was originally stored in the spacetime curvature surrounding the two black holes, distributed across vast regions of space according to Einstein's field equations. When this distributed energy concentrates into propagating gravitational waves, it undergoes a form of phase transition that affects the entropy balance of the entire system. The waves themselves carry entropy related to their information content, while the final black hole develops new internal correlations that weren't present in the original separated black holes. Understanding this entropy redistribution requires sophisticated tools from quantum field theory and curved spacetime. The observational detection of these energy releases provides unprecedented opportunities to test our understanding of black hole thermodynamics in real time. Each gravitational wave detection tells us the exact amount of energy radiated during merger, allowing direct calculation of the mass and entropy of the final black hole. Comparing these observations with theoretical predictions tests our understanding of how entropy behaves during the most extreme physical processes in the universe. Perhaps most remarkably, the energy scales involved in black hole mergers approach the fundamental limits imposed by general relativity itself. The Planck energy, approximately 10 GeV, derived from fundamental constants, represents the scale where quantum gravitational effects become important, while individual black hole mergers don't quite reach these energies. They approach close enough to probe the boundary between classical general relativity and quantum gravity. This proximity to fundamental energy scales suggests that black hole mergers might serve as natural laboratories for testing theories of quantum gravity. The energy densities reached during the final moments of merger approach those present during the first moments after the Big Bang, potentially revealing connections between black hole thermodynamics and cosmological entropy. The conversion of binding energy to gravitational radiation during black hole mergers thus represents far more than a cosmic fireworks display. It's a demonstration of mass energy equivalence operating at cosmic scales, a test of general relativity in its most extreme regime, and a window into the quantum nature of spacetime itself. Most importantly for our story, it provides the energy source that drives the dramatic entropy increases we observe during these mergers. Understanding how binding energy converts to gravitational radiation, and how this process affects the entropy budget of merging black holes, brings us closer to answering fundamental questions about the nature of information, energy, and thermodynamics in our universe. The impossible energies released during these mergers aren't just cosmic spectacles, they ray clues to some of the deepest mysteries in physics. Chapter 4: Quantum Horizons. The event horizon of a black hole represents one of the most mysterious boundaries in physics, a point of no return where our understanding of space-time and information reaches its limits. Yet recent advances in quantum field theory and string theory suggest that what we once thought of as empty space surrounding black holes actually teems with quantum activity. That fundamentally changes how we understand entropy and information during merger events. According to classical general relativity, an event horizon is simply a mathematical surface marking the boundary beyond which escape becomes impossible. Nothing special happens locally as you cross this boundary: no wall, no barrier, no dramatic change in the local physics. This is the equivalence principle in action. Free fall feels the same everywhere, whether you're falling toward Earth or falling past a black hole's event horizon into its interior. But quantum mechanics reveals a far richer and stranger picture. The vacuum state of quantum fields near black hole horizons is actually empty. It is filled with quantum fluctuations that create virtual particle pairs throughout all of space. Near the event horizon, something remarkable happens to these fluctuations. They become entangled across the horizon boundary in ways that fundamentally alter the information content and entropy of the entire system. Stephen Hawking's original calculation of black hole radiation emerged from studying these quantum fluctuations. Virtual particle pairs near the horizon occasionally become real, with one particle falling into the black hole while its partner escapes as Hawking radiation. But this simple picture, while capturing the essential physics, misses the profound quantum entanglement structure that develops between the interior and exterior of the black hole. The quantum state of the Hawking radiation is entangled with quantum degrees of freedom inside the black hole in ways that preserve total quantum information while creating correlations that span the event horizon. These correlations contribute to the total entropy of the black hole system and play a crucial role in understanding how entropy increases during merger events. When two black holes approach each other, their individual quantum horizon structures begin to interact and merge in ways that dramatically amplify these quantum effects. The near-horizon regions of each black hole contain entangled quantum states that suddenly find themselves in proximity to the entangled states of the other black hole. The result is a quantum superposition of entanglement patterns that didn't exist when the black holes were widely separated. This quantum entanglement across horizons reveals deep connections to the holographic principle, the idea that all information contained within a volume of space can be encoded on the boundary of that volume. For black holes, this suggests that the entropy we associate with their interior is actually encoded in quantum correlations on the event horizon surface itself. The holographic principle emerged from string theory studies of black holes in higher dimensional spacetimes, but its implications extend far beyond string theory. If the principle is correct, then the enormous entropies of black holes don't represent information hidden inside the black hole where we can never access it. Instead, they represent information encoded in quantum correlations on the horizon surface that we can, in principle, decode through sufficiently sophisticated measurements. During black hole mergers, these holographically encoded quantum states undergo dramatic reorganization. As the event horizons approached, deformed, and eventually merged, the quantum information encoded on their surfaces must somehow combine, reorganize, and redistribute itself onto the surface of the final black hole. This process requires creating new quantum entanglement patterns that didn't exist in either original black hole. The creation of new entanglement patterns during merger directly increases the total entropy of the system. Each new quantum correlation contributes to the number of possible microscopic states consistent with the macroscopic properties we observe, the mathematics of entanglement entropy, developed in quantum information theory, provides tools for calculating exactly how much entropy increase results from these new quantum correlations. Recent work in ADS-CFT correspondence, a precise mathematical realization of the holographic principle, has revealed that black hole mergers in higher dimensional anti-de Sitter spacetime correspond to thermalization processes in lower dimensional quantum field theories. These calculations show explicitly how quantum entanglement grows during merger events, providing concrete examples of entropy increase that we can calculate from first principles. The quantum nature of event horizons also resolves long-standing puzzles about information conservation during black hole formation and evaporation. If black holes eventually evaporate through Hawking radiation, as theory predicts, what happens to the information that fell into them? The quantum entanglement structure of horizons suggests that this information never truly disappears. It remains encoded in correlations between the outgoing Hawking radiation and the quantum state of the black hole interior. This resolution of the black hole information paradox has profound implications for understanding merger events. When two black holes merge, the information content of both black holes must somehow be preserved in the final state. The quantum entanglement structure of horizons provides a mechanism for this information preservation, while simultaneously explaining how new entropy can be created through the generation of new quantum correlations. The experimental detection of gravitational waves from black hole mergers provides our first opportunity to test these quantum horizon effects observationally. The detailed waveforms of gravitational radiation carry subtle imprints of the quantum structure of the merging horizons, while current detectors can't resolve these quantum effects directly. Future space-based gravitational wave observatories may be sensitive enough to detect quantum signatures in merger waveforms. The quantum nature of black hole horizons also connects to fundamental questions about the nature of spacetime itself, if horizons are quantum mechanical rather than classical. This suggests that spacetime emerges from more fundamental quantum degrees of freedom perhaps. Quantum entanglement itself, this idea, called emergent spacetime, represents one of the most active areas of research in quantum gravity. From this perspective, black hole mergers aren't just cosmic collisions, they are quantum information processing events where entanglement patterns reorganize and new quantum correlations emerge. The entropy increase during merger reflects the creation of new quantum entanglement patterns that encode information about the merger process itself. Understanding quantum horizons requires tools from quantum field theory, quantum information theory, and string theory working together. The mathematical structure is subtle and complex, involving concepts like entanglement entropy, quantum error correction, and holographic duality. Yet the physical picture that emerges is elegant and beautiful. Black hole horizons are quantum information processing surfaces that encode, store, and manipulate information in ways that reveal deep connections between gravity, quantum mechanics, and information theory. The quantum horizon picture suggests that black hole mergers represent some of the most sophisticated information processing events in the universe. As horizons merge and quantum entanglement patterns reorganize, these systems perform quantum computations that would dwarf the capabilities of any conceivable classical computer. The entropy increase during merger reflects the complexity of these quantum information processing events. This quantum understanding of horizons opens new possibilities for understanding black hole interiors, the nature of singularities, and the ultimate fate of information in our universe. It suggests that black holes aren't cosmic dead ends but cosmic quantum computers processing information in ways we are only beginning to comprehend. Chapter 5 Information Paradox. At the heart of black hole physics lies a paradox so profound it has divided physicists for decades and continues to reshape our understanding of quantum mechanics, general relativity, and the fundamental nature of reality itself. The black hole information paradox asks a seemingly simple question: what happens to information when it falls into a black hole? The answer forces us to confront the most basic assumptions about causality, determinism, and the conservation of information in our universe. The paradox emerges from the collision between two of our most successful physical theories. General relativity tells us that information falling past a black hole's event horizon continues to exist inside the black hole, eventually reaching the central singularity where our equations break down. Quantum mechanics, however, demands that information must be conserved. The total information content of any closed system can never decrease, only increase or remain constant. These two requirements seem compatible until we consider Stephen Hawking's discovery that black holes evaporate through quantum radiation. As a black hole emits Hawking radiation and gradually shrinks, it eventually disappears completely, leaving behind only a bath of thermal radiation. If the information that fell into the black hole cannot escape before evaporation is complete, it would appear to be permanently destroyed, violating one of the most fundamental principles of quantum mechanics. Hawking originally argued that information is indeed destroyed during black hole evaporation, representing a fundamental breakdown of quantum mechanics in the presence of strong gravitational fields. This proposal shocked the physics community because information destruction would undermine the mathematical foundation of quantum theory itself. Without information conservation, quantum mechanics loses its predictive power and becomes fundamentally incomplete. The stakes of this paradox extend far beyond academic debate. If information can be destroyed in black holes, it calls into question whether our universe operates according to deterministic laws. Quantum mechanics may be probabilistic in its predictions, but it's deterministic in its evolution given complete information about a quantum system at one time. The theory predicts its complete state at any future time. Information destruction would shatter this deterministic foundation. Leonard Susskind and Gerard T. Hooft proposed a radical solution known as the holographic principle. They suggested that information falling into a black hole is actually encoded on the event horizon surface, never entering the interior at all. From this perspective, black holes are holographic storage devices that encode three-dimensional information on two-dimensional surfaces. Much like the holograms we create with laser light, the holographic principle received dramatic confirmation through the DS-CFT correspondence discovered by Juan Mel de Sena in 1997. This mathematical duality precisely describes how gravity in a higher dimensional space corresponds to quantum field theory on its boundary surface. Black holes in the higher dimensional space correspond to thermal states in the boundary theory, providing concrete examples of how gravitational physics emerges from quantum information processing. But the holographic resolution of the information paradox creates new puzzles about what happens during black hole mergers. If two black holes each store information holographically on their event horizon surfaces, how does this information combine when the horizons merge? The process requires creating new holographic encodings that preserve all the information from both original black holes while accommodating the new quantum correlations created during merger. Recent work on quantum error correction has revealed deep connections between black hole physics and information theory. The holographic encoding of information on black hole horizons resembles quantum error correcting codes that protect information against decoherence and loss during merger events. These quantum codes must somehow merge and reorganize while preserving all encoded information. The merger process creates new quantum entanglement patterns that didn't exist in either original black hole. These new entanglements represent additional information about the merger process itself, information about how the black holes approached their relative orientations, the details of their gravitational wave emission. This new information contributes to the total entropy of the final black hole, helping explain why merger entropy exceeds the sum of the original entropies. The firewall paradox, proposed by Ahmed Al-Mahari and colleagues in 2012, adds another layer of complexity. If information falling into a black hole must be rapidly released in Hawking radiation to preserve quantum mechanics, then the event horizon cannot be a smooth, empty region as general relativity suggests. Instead, it must be a firewall of high-energy quanta that would incinerate any infalling observer. This paradox forces us to choose between fundamental principles: either general relativity as prediction of smooth event horizons is wrong, or quantum mechanics requirement of information conservation is wrong, or our understanding of how observers experience black hole spacetime is fundamentally flawed. Each option requires abandoning deeply held beliefs about the nature of spacetime and information. During black hole mergers, the firewall paradox becomes even more acute. If each black hole harbors a firewall at its event horizon, what happens when these firewalls approach and merge? The answer may require entirely new physics beyond both general relativity and standard quantum mechanics, perhaps involving modifications to spacetime itself at microscopic scales. String theory offers one approach to resolving these paradoxes through the concept of black hole complementarity. From this perspective, information falling into a black hole has two equivalent descriptions. It either falls through the event horizon into the interior from the perspective of an infalling observer, or is encoded on the horizon surface and later emerges in Hawking radiation from the perspective of an external observer. Both descriptions are correct within their respective reference frames. Loop quantum gravity proposes a different resolution based on quantum modifications to spacetime geometry. In this theory, the classical singularity at the black hole's center is replaced by a quantum bounce that eventually reverses the gravitational collapse. Information that appears to fall into the black hole actually emerges from a quantum white hole in a distant future spacetime, preserving information conservation through quantum tunneling effects. The experimental detection of gravitational waves from black hole mergers provides new opportunities to test these theoretical ideas. The detailed waveforms of merger events carry information about the quantum structure of event horizons and the information processing that occurs during merger. Future gravitational wave detectors may be sensitive enough to detect quantum signatures that could distinguish between different resolutions of the information paradox. Perhaps most remarkably, The information paradox suggests that black holes are not cosmic dead ends but cosmic information processors operating according to principles we are only beginning to understand. ND. The enormous entropies of black holes may represent the computational capacity of the universe's most sophisticated information storage and processing systems. Black hole mergers would then represent cosmic computations of unimaginable complexity. The resolution of the information paradox will likely require synthesis of ideas from general relativity, quantum mechanics, quantum information theory, and perhaps entirely new physics. Black hole mergers serve as natural laboratories where these ideas can be tested against observation, potentially revealing whether information truly is conserved in our universe and how quantum mechanics operates in the presence of strong gravitational fields. Understanding how information behaves during black hole mergers brings us closer to resolving one of the deepest mysteries in physics while simultaneously revealing new puzzles about the nature of entropy, computation, and reality itself. The answer may reshape our understanding of what it means for information to exist and how the universe processes and preserves the quantum information that underlies all physical reality. Chapter 6: Gravitational Memory. When do black holes merge and send gravitational waves rippling across the universe? They leave behind something unexpected, a permanent change in the geometry of spacetime itself that persists long after the waves have passed. This phenomenon, called gravitational wave memory, represents one of the most subtle yet profound effects predicted by general relativity. And its connection to black hole entropy reveals deep truths about how information and energy propagate through the fabric of reality. And like electromagnetic waves, which oscillate around a baseline and return to their original state after passing, gravitational waves can induce permanent displacements in the distances between freely falling objects. This memory effect arises from the nonlinear nature of Einstein's field equations. Gravitational waves themselves carry energy and momentum, which creates additional gravitational effects that accumulate over time rather than averaging to zero. Imagine to test particles floating in space as gravitational waves from a distant black hole merger pass through them. The waves alternately stretch and compress the distance between the particles in a characteristic pattern, but when the waves have completely passed, the particles don't return to their original separation. Instead, they remain permanently displaced by a tiny amount that depends on the total energy carried away by the gravitational waves. This displacement memory encodes information about the merger event that persists indefinitely after the waves themselves have propagated away. The magnitude and direction of the memory effect depends on the masses, spins, and orbital parameters of the merging black holes, providing a permanent record of the merger embedded in the geometry of spacetime itself. The mathematical description of gravitational wave memory emerged from detailed studies of the asymptotic structure of spacetime at large distances from gravitating sources. When Joseph Zlakor, Demetrios Christodoulou, and others worked out the mathematics in the 1980s and 1990s, they discovered that the memory effect is intimately connected to the conservation of energy and momentum during gravitational wave emission. The connection to entropy becomes clear when we recognize that gravitational wave memory represents a form of information storage in spacetime geometry itself. Each merger event leaves a unique signature in the surrounding spacetime, a permanent displacement field that encodes details about the merger process. This information storage contributes to the total entropy of the spacetime region, providing a mechanism for entropy increase that extends far beyond the merged black hole itself. During black hole mergers, the memory effect operates on multiple scales simultaneously. The most dramatic memory comes from the burst of gravitational waves during the final merger and ringdown phases, when enormous amounts of energy are radiated away in milliseconds. But there's also a subtle memory effect from the inspiral phase, gradually accumulating over the millions of years leading up to merger as the black holes spiral together. The burst memory dominates for most practical purposes, creating displacement jumps that scale with the total energy radiated in gravitational waves. For the merger detected as GW15091, for this memory effect would displace test particles by approximately 10 to 21 meters at a distance of 1 billion light-years, impossibly small by everyday standards. yet precisely calculable from general relativity and potentially detectable by future gravitational wave observatories. What makes memory particularly fascinating is its connection to asymptotic symmetries of spacetime. The Bondi-Metzner-Sachs BMS group describes the symmetries of spacetime at no infinity essentially. The symmetries that remain after accounting for all possible coordinate transformations that do it change the physical content of the theory. Gravitational wave memory is associated with these BMS symmetries in ways that connect the geometry of spacetime to the information content of gravitational radiation. This connection suggests that gravitational wave memory serves as a kind of cosmic information storage system. Each gravitational wave burst from a black hole merger permanently alters the surrounding spacetime geometry, creating a historical record that persists indefinitely. The accumulated memory effects from countless merger events throughout cosmic history form a complex pattern of permanent spacetime deformations that encode information about the universe's gravitational wave history. The thermodynamic implications are profound. If gravitational wave memory represents permanent information storage in spacetime geometry, then the emission of gravitational waves doesn't just carry energy away from a system, it also creates no formation storage capacity in the surrounding spacetime. This information storage contributes to the total entropy of the universe, providing a mechanism for cosmic entropy increase that operates through the modification of spacetime geometry itself. Recent theoretical work has revealed connections between gravitational wave memory and quantum entanglement across cosmic distances. The permanent spacetime deformations created by memory effects may generate quantum correlations between widely separated regions of space, creating a form of cosmic entanglement that contributes to the universe's total entropy in ways we are only beginning to understand. The detection of gravitational wave memory presents extraordinary experimental challenges. Current ground-based detectors like LIGO and Virgo are primarily sensitive to the oscillating components of gravitational waves, not the permanent displacement effects of memory. However, future space-based detectors like LISA laser interferometer space antenna may be capable of measuring memory effects from supermassive black hole mergers. The experimental signature of memory would appear as a permanent change in the arm lengths of a gravitational wave detector after a merger event. Instead of the detector arms oscillating around their original length and returning to baseline, they would settle into a new equilibrium configuration with slightly different lengths. Detecting this effect requires extraordinary stability and precision over timescales much longer than the merger event itself. Pulsar timing arrays networks of precisely timed radio pulsars distributed across the galaxy offer another potential avenue for detecting gravitational wave memory. These natural cosmic clocks are sensitive to the permanent changes in spacetime geometry that memory effects create, potentially allowing detection of memory from supermassive black hole mergers throughout the universe. The cosmological implications of gravitational wave memory extend to the largest scales of space and time. Over cosmic history, countless black hole mergers have occurred throughout the universe, each leaving its permanent signature in spacetime geometry. The accumulated memory effects from all these mergers create a complex background of spacetime deformations that carries information about the universe's gravitational wave history. This cosmic memory background represents a form of fossil gravitational radiation permanent modifications to spacetime that preserve information about long-past merger events. Like the cosmic microwave background radiation that carries information about the early universe, the gravitational wave memory background carries information about black hole formation and merger throughout cosmic time. Understanding gravitational wave memory also connects to fundamental questions about the nature of spacetime itself. If spacetime can store information permanently through memory effects, this suggests that geometry itself is a dynamic, information-carrying medium rather than a passive stage for physical events. This perspective aligns with ideas from quantum gravity theories that propose spacetime emerges from more fundamental information-theoretic structures. The study of gravitational wave memory thus reveals that black hole mergers create permanent changes extending far beyond the merged black hole itself. These changes represent a form of cosmic information processing where merger events encode their signatures into the geometry of spacetime, creating an ever-growing library of gravitational information that contributes to the universe's total entropy in profound and subtle ways. As we develop more sensitive gravitational wave detectors and more sophisticated theoretical understanding, gravitational wave memory may provide crucial insights into how information, entropy, and spacetime geometry interconnect at the deepest levels of physical reality. Chapter 7: Holographic Truth. The holographic principle represents one of the most revolutionary ideas in modern physics, the notion that all the information contained in any volume of space can be encoded on the boundary surface of that volume, much like a hologram encodes three-dimensional images on two-dimensional film. For black holes, this principle suggests something extraordinary. The enormous entropy we associate with their interiors is actually encoded on their two-dimensional event horizon surfaces, transforming our understanding of how information and entropy behave during merger events. The principle emerged from Jacob Bekenstein's insight that black hole entropy scales with surface area rather than volume, combined with Gerard T. Hooft and Leonard Susskind's resolution of the black hole information paradox. If information falling into a black hole must somehow be preserved to maintain quantum mechanical consistency, and if black hole entropy depends on surface area, then perhaps the information never actually enters the black hole interior but is instead encoded on the horizon surface itself. This encoding process operates according to principles reminiscent of optical holography, but far more fundamental. In optical holograms, interference patterns on a two-dimensional surface contain enough information to reconstruct a full three-dimensional image when illuminated properly. Similarly, the quantum fluctuations on a black hole's event horizon contain enough information to reconstruct the complete quantum state of everything that has ever fallen into the black hole. The mathematical realization of this principle came through Juan Maldacena's discovery of ADS-CFT correspondence in 1997, a precise mathematical duality between gravitational theories and higher-dimensional anti-de Siderat space and conformal field theories CFT living on the boundary of that space. In this correspondence, black holes in the bulk gravitational theory correspond to thermal states in the boundary quantum field theory, providing concrete examples of holographic information encoding. For black hole mergers, the holographic principle reveals that what appears to be a collision between three-dimensional objects is actually a reorganization of information encoded on two-dimensional faces. When two black holes approach each other, their holographic encodings begin to interact and merge in ways that preserve all information, while creating new quantum correlations that didn't exist in either original system. The merger process requires sophisticated quantum error correction to ensure that no information is lost during the violent combination of two holographic encodings. The quantum states encoded on each event horizon must be carefully combined and redistributed onto the surface of the final black hole, creating new entanglement patterns that accommodate information from both progenitors plus new information generated during the merger process itself. This holographic reorganization provides a natural explanation for why black hole mergers increase entropy beyond the simple sum of the original entropies. The merger creates new quantum correlations between previously independent holographic encodings, and these new correlations represent additional information that contributes to the total entropy of a system. From this perspective, entropy increase during merger reflects the complexity of merging to quantum information storage systems. The holographic description also resolves potential paradoxes about information flow during merger events. Since information is encoded on horizon surfaces rather than stored in black hole interiors, the merger doesn't require moving information from interior to interior. Instead, it involves reorganizing surface encodings in ways that preserve all information while accommodating new quantum correlations created during the merger process. Recent work in quantum error correction has revealed deep connections between holographic encodings and classical error-correcting codes used in computer science and telecommunications. The redundancy built into holographic encodings resembles the redundancy used in quantum error-correcting codes to protect information against noise and decoherence during mergers. This error correction machinery ensures that information is preserved even during the violent reorganization of holographic encodings. The CFT correspondence allows explicit calculation of entropy changes during merger-like processes in simplified toy models, when black holes merge in anti-de Sitter spacetime. The corresponding boundary field theory undergoes thermalization processes that create new quantum entanglements and increase the total entropy of the system. These calculations provide concrete examples of how holographic encodings merge while preserving information and increasing entropy. The holographic principle also suggests that black hole mergers are fundamentally quantum information processing events rather than simply classical gravitational collisions. The complex quantum algorithms required to merge to holographic encodings while preserving all information and maintaining quantum error correction represent some of the most sophisticated computation processes in the known universe. From this perspective, black holes are cosmic quantum computers that store and process information according to holographic principles. Their enormous entropies reflect their computational capacity, the number of distinct quantum states they can encode and manipulate. Black hole mergers then represent the combination of two quantum computers into a single, more powerful system capable of storing and processing even larger amounts of information. The holographic understanding of black hole mergers connects to broader questions about the nature of spacetime and reality itself. If three-dimensional physics can be completely described by two-dimensional holographic encodings, this suggests that the dimensionality we experience may be emergent rather than fundamental. Space itself might emerge from quantum information processing on lower dimensional surfaces. This emergence of spacetime from information processing has profound implications for understanding consciousness, causality, and the nature of reality. If space and time emerge from information processing, then the fundamental constituents of reality might be computational rather than material bits of information rather than particles of matter. The experimental verification of holographic principles in black hole mergers presents extraordinary challenges. The holographic encodings exist at quantum scales far below anything we can directly observe, and information processing occurs through quantum correlations that span cosmic distances. However, the gross properties of merger events, their energy output, final black hole parameters, and gravitational wave signatures all depend on the underlying holographic physics. Future advances in quantum information theory and gravitational wave astronomy may provide indirect tests of holographic principles during merger events. The precise waveforms of gravitational radiation carry subtle imprints of the quantum information processing that occurs during holographic reorganization. Detecting these quantum signatures would provide the first direct evidence that black holes operate according to holographic principles. The holographic principle also suggests new approaches to understanding the black hole information paradox and the firewall controversy. If information is encoded holographically rather than stored in black hole interiors, then many of the paradoxes that arise from thinking about information falling into black holes may be artifacts of incorrect conceptual frameworks rather than genuine physical contradictions. Perhaps most remarkably, the holographic understanding of black holes suggests that entropy increase during mergers reflects the fundamental information processing capacity of our universe. Each merger event represents a cosmic computation that reorganizes quantum information on cosmic scales, creating new patterns of entanglement and correlation that increase the universe's capacity for storing and processing information. The holographic principle thus transforms our understanding of black hole mergers from cosmic catastrophes into cosmic information processing events. The entropy increases we observe reflect not just thermodynamic principles but computational principles, the universe's ongoing effort to organize, store, and process the quantum information that underlies all physical reality. Understanding black hole mergers through holographic principles brings us closer to a unified description of gravity, quantum mechanics, and information theory, a description that may ultimately reveal the computational architecture underlying the fabric of spacetime itself. Chapter 8: Temporal Arrows. Time's arrow, the irreversible flow from past to future that governs every aspect of our existence, finds its most dramatic expression in the merger of black holes. These cosmic events represent the universe's most spectacular demonstrations of thermodynamic irreversibility. where enormous amounts of ordered gravitational potential energy transform into disordered thermal radiation and increased black hole entropy. Understanding how black hole mergers amplify time's arrow reveals profound connections between cosmology, thermodynamics, and the fundamental structure of causality itself. The thermodynamic arrow of time emerges from the statistical nature of entropy and the second law of thermodynamics. In any isolated system, entropy tends to increase over time because there are vastly more disordered arrangements of matter and energy than ordered ones. A broken egg never spontaneously reassembles, not because the laws of physics forbid it, but because the probability is so astronomically small that it never occurs in practice. Black hole mergers represent this principle operating at cosmic scales. Two black holes orbiting each other in a bound system possess enormous amounts of ordered gravitational potential energy. This energy exists in a highly organized form, a specific orbital configuration that allows the black holes to circle each other indefinitely. During merger, this ordered energy transforms into disordered thermal radiation and increased black hole entropy, representing an irreversible increase in cosmic disorder. The irreversibility of black hole mergers becomes even more striking when we consider the time reverse process. Imagine watching a movie of a black hole merger played backward. Gravitational waves converge from across the universe to focus precisely on a single black hole, causing it to split into two smaller black holes that then spiral apart. While this reverse process violates no fundamental laws of physics, it requires such precisely coordinated initial conditions that it never occurs naturally. The probability of spontaneous black hole fission is so infinitesimally small that it effectively never happens, even over cosmological timescales. This represents the thermodynamic arrow of time in its purest form, the overwhelming statistical preference for processes that increase rather than decrease entropy. Black hole mergers amplify this preference because they involve such enormous entropy changes operating over such vast scales of space and time. The connection between black hole mergers and time's arrow extends beyond simple entropy increase to more subtle aspects of temporal asymmetry. The gravitational wave emission during merger creates correlations between the final black hole state and the radiation field that propagates away at light speed. These correlations encode information about the merger process in ways that distinguish past from future. When gravitational waves from a merger reach Earth, they carry information about the black hole's properties millions or billions of years in the past. This information flow from past to future represents another manifestation of time's arrow, the tendency for information to propagate from causes to effects rather than the reverse. The wave patterns we detect encode the history of the merger, creating an irreversible connection between past events and present observations. The thermodynamic description of black hole mergers also reveals deep connections to the cosmological arrow of time. Our universe began in an extraordinarily low entropy state shortly after the Big Bang, with matter and energy distributed much more uniformly than they are today. Gravity has since amplified small initial density fluctuations into the complex structure we observe: stars, galaxies, black holes, and the cosmic web of dark matter. Black hole formation and merger represent key steps in this cosmic evolution toward higher entropy. When massive stars collapse to form black holes, gravitational potential energy converts to thermal radiation and black hole entropy. When black holes merge, orbital energy converts to gravitational radiation and further entropy increase. These processes drive the universe's evolution from its initial low entropy state toward the high entropy heat death that thermodynamics predicts. Yet black hole mergers also reveal subtle violations of naive time reversal symmetry that arise from quantum effects and general relativistic gravity. The Hawking radiation emitted by black holes breaks time reversal symmetry in subtle ways related to the quantum mechanical nature of particle creation in curved spacetime during merger events. These quantum effects contribute to the overall irreversibility of the process. The memory effects of gravitational wave radiation also contribute to temporal asymmetry. After gravitational waves pass through a region of space, they leave permanent changes in the geometry of spacetime that provide a lasting record of the merger event. These memory effects accumulate over cosmic time, creating an ever-growing library of information about past merger events encoded in spacetime geometry itself. The question of whether time's arrow is fundamental or emergent remains one of the deepest mysteries in physics. Black hole mergers provide natural laboratories for studying this question because they involve such extreme conditions and such dramatic entropy changes. The precise mechanisms by which merger events amplify temporal asymmetry may provide clues about whether time's arrow emerges from statistical mechanics or reflects more fundamental asymmetries. In the laws of physics, recent work in quantum gravity suggests that time itself might emerge from more fundamental timeless quantum mechanical processes. From this perspective, the arrow of time reflects the way quantum entanglement patterns evolve and complexify over cosmic scales. Black hole mergers represent dramatic reorganizations of quantum entanglement that create new patterns of correlation extending across vast regions of spacetime. The ADS-CFT correspondence provides concrete examples of how time's arrow emerges in holographic theories, when black holes merge in anti-de Sitter spacetime. The corresponding boundary field theory undergoes irreversible thermalization processes that create new quantum entanglements and increase entropy. These processes demonstrate how temporal asymmetry emerges from quantum information processing rather than being imposed as an external condition. The experimental study of black hole mergers through gravitational wave astronomy provides unprecedented opportunities to test our understanding of time's arrow in extreme gravitational fields. The detailed waveforms of merger events encode information about how entropy increases, how information propagates, and how quantum correlations evolve during these cosmic events. Future advances in gravitational wave detection may allow us to observe time asymmetry directly through the subtle asymmetries in merger waveforms. The spiral, merger, and ring-down phases each contribute differently to entropy production, creating temporal signatures that reflect the underlying irreversibility of the merger process. Perhaps most profoundly, black hole mergers suggest that time's arrow is not simply a feature of thermodynamic systems but a fundamental aspect of how information, energy, and spacetime interact at the deepest levels of physical reality. The irreversible increase of entropy during merger reflects the universe's ongoing evolution towards states of greater complexity and information content. The study of temporal asymmetry in black hole mergers also connects to questions about the nature of consciousness and observation. The fact that we can observe merger events only through their paths like cones through gravitational waves and electromagnetic radiation that reach us from past events reflects the causal structure of spacetime and the fundamental asymmetry between past and future. Understanding how black hole mergers amplify time's arrow brings us closer to resolving fundamental questions about the nature of time, causality, and the evolution of cosmic complexity. These merger events represent the universe's most dramatic demonstrations of irreversibility, providing natural laboratories for studying how temporal asymmetry emerges from and contributes to the ongoing evolution of cosmic structure and information. The arrow of time that governs our everyday experience reaches its most spectacular expression in the merger of black holes, where cosmic scalar reversibility creates the entropy increases that drive the universe's evolution from its ordered beginning toward its disordered future. Chapter 9, Spacetime Fabric. Spacetime is not the static, unchanging stage that Newton imagined, but a dynamic, elastic fabric that bends, stretches, and vibrates in response to mass and energy. Black hole mergers represent the most violent distortions this fabric has ever experienced, creating ripples that race across the universe while fundamentally altering the geometry of space and time itself. Understanding how these distortions relate to entropy reveals deep truths about the relationship between geometry, information, and the physical laws that govern our reality. Einstein's general relativity describes spacetime as a four-dimensional manifold where mass and energy curve the geometry, and this curvature guides the motion of matter and energy. The famous phrase "matter tells spacetime how to curve," and "curved spacetime tells matter how to move" captures the intimate connection between geometry and physics that makes general relativity so different from all previous theories of gravity. When two black holes orbit each other, they create a complex pattern of spacetime curvature that extends far beyond their individual event horizons. Their combined gravitational field warps space and time in ways that depend on their masses, spins, separation, and orbital parameters as they spiral together. This warped geometry evolves dynamically, creating the time-varying gravitational fields that generate gravitational wave radiation. The mathematics describing this evolving geometry requires Einstein's field equations in their full, nonlinear glory. These equations relate the curvature of spacetime at each point to the mass, energy, and momentum present at that point. For black hole mergers, the curvature becomes so extreme that space and time themselves participate in the dynamics, carrying energy and momentum away from the system in the form of gravitational waves. This participation of geometry in physical dynamics represents one of the most profound aspects of general relativity, and like electromagnetic waves, which propagate through spacetime but don't directly alter its structure. Gravitational waves are distortions of spacetime itself. When these waves carry away energy from a merging black hole system, they're literally carrying away pieces of the spacetime geometry that contain that energy. The relationship between spacetime curvature and entropy becomes apparent when we consider that geometry itself can store and process information. The precise pattern of curvature on a black hole encodes information about all the matter and energy that contributed to its formation. This information is distributed throughout the curved spacetime geometry according to Einstein's field equations, creating a form of geometric information storage. During black hole mergers, the collision and reorganization of these geometric information patterns creates new correlations and entanglements that didn't exist in the original separated black holes. The merger process fundamentally alters the topology and geometry of spacetime, creating new ways for information to be stored and correlated across the resulting curved geometry. These new geometric correlations contribute to the entropy increase observed during merger events. The concept of emergent spacetime, developed in string theory and quantum gravity research, suggests that geometry itself might emerge from more fundamental quantum information processing. From this perspective, the curved spacetime around black holes represents the macroscopic manifestation of quantum entanglement patterns operating at microscopic scales. Black hole mergers would then represent the reorganization of these entanglement patterns in ways that create new geometric structures. The holographic principle provides another lens for understanding the relationship between spacetime geometry and information storage. If all the information in a volume of space can be encoded on its boundary surface, then the curved geometry of that volume emerges from the quantum correlations encoded on the boundary. Black hole mergers involve the reorganization of these boundary encodings in ways that create new geometric structures while preserving all information. Recent work in tensor networks and quantum error correction has revealed concrete mathematical connections between quantum information processing and emergent geometry. These approaches show how geometric properties like distances, angles, and curvatures can emerge from the entanglement structure of quantum information. Black hole mergers represent dramatic reorganizations of these quantum entanglement patterns that create new emergent geometries. The experimental detection of gravitational waves provides direct observation of spacetime curvature and its dynamic evolution. When LIGO detects a gravitational wave, it's measuring the actual stretching and compression of space itself as the wave passes through the detector. These measurements provide unprecedented insight into how spacetime geometry evolves during black hole mergers and how this evolution relates to energy and information transport. The gravitational wave memory effect represents perhaps the most striking example of how black hole mergers permanently alter spacetime geometry. After the waves from a merger have passed, the geometry of spacetime retains permanent changes that encode information about the merger event. This geometric memory serves as a form of information storage that persists indefinitely, contributing to the total entropy of the spacetime region. Understanding spacetime as an information-carrying medium also connects to fundamental questions about the nature of physical law itself. If geometry emerges from information processing, then the apparently fundamental laws of general relativity might actually be effective descriptions of underlying quantum information dynamics. From this perspective, Einstein's field equations describe how information processing creates geometric structures rather than how geometry responds to matter and energy. The quantum geometry of spacetime near black hole horizons reveals additional connections between curvature and information. Quantum fluctuations of the spacetime metric create virtual geometric structures at microscopic scales, quantum bubbles of curved space that constantly appear and disappear due to quantum uncertainty. During black hole mergers, these quantum geometric fluctuations play crucial roles in creating the new quantum correlations that increase the system's total entropy. Loop quantum gravity provides one approach to understanding quantum spacetime geometry, proposing that space itself is discrete at the smallest scales composed of quantum geometric building blocks called spin networks. From this perspective, black hole mergers involve the reorganization of these discrete geometric structures in ways that create new quantum correlations and increase entropy through purely geometric mechanisms. String theory offers another approach through the concept of emergent spacetime, where geometry emerges from the dynamics of fundamental strings moving through higher dimensional spaces. Black holes in string theory correspond to bound states of strings that create effective geometric structures. Mergers involve the combination and reorganization of these string configurations in ways that create new geometric patterns while preserving all quantum information. The connection between geometry and entropy in black hole mergers also illuminates broader questions about the nature of space and time. If space-time geometry can store and process information, this suggests that our familiar three-dimensional space and one-dimensional time might emerge from more fundamental information theoretic structures operating according to computational rather than geometric principles. The study of black hole mergers thus reveals spacetime itself as an active participant in physical processes rather than a passive container for matter and energy. The fabric of reality bends, stretches, vibrates, and permanently reorganizes itself during these cosmic events, creating new geometric patterns that store and process information in ways that contribute directly to the universe's total entropy. This geometric understanding of entropy increase during black hole mergers connects to the deepest questions in physics: the nature of space and time, the emergence of physical law from information processing, and the relationship between quantum mechanics and gravity. As we develop more sophisticated theoretical tools and more sensitive experimental probes, our understanding of spacetime as an information processing fabric continues to reveal new layers of cosmic complexity and beauty. The ripples in spacetime that we detect as gravitational waves represent more than cosmic signals, they're direct observations of information processing at the most fundamental level of physical reality.